Hello there. So last week we talked about the importance of prime factoring, right? And we talked about how to prime factor and how to just get into it. Today we're going to start our foray into why bother? What are some of the key important things we can do once we have the prime factorization of any number? So today's going to be part one, which is finding the LCM and GCF. And honestly, this is a majority of what we will ask you to do once you have your prime factors. So knowing this and understanding this is going to be really critical when we move forward and actually talk about this. Okay? All right. So let's do this. All right. So the least common multiple, to find the LCM, well, first of all, let's talk about what exactly the LCM is, right? The LCM is referred to as the least common multiple, right? And what that means is that when you list out the multiples, you're going to pick the smallest number that's common among the multiples of both of those other numbers. So let's go ahead and try this. I have a sample problem here with 6 and 8, right? So how would we attempt this? Well, we start by writing out the multiples of both of those numbers, right? So if you think to yourself, what are the multiples of 6? Well, let's see. So here's 6, right? And we think to ourselves, okay, well, what's 6 times 1? Well, 6 times 1 is equal to 6, right? And 6 times 2 is equal to 12. 6 times 3 is equal to 24. Sorry, 18. And 6 times 4 is 24. We don't need any more, but I'm going to do one more, which is going to be 6 times 5, which is 30. So we have this, let me just fix that bracket. We have this repertoire of multiples for 6, right? So again, you're just doing 6 times 1, 6 times 2, 6 times 3, 6 times 4, 6 times 5, right? So we have here 6 times 1, 2, 3, 4, and 5. Now let's do the same thing with 8. So for 8, again, we're going to start with 8 times 1, which is of course 8. Then we have 8 times 2, which is 16. Then we have 8 times 3, which is 24. And we're going to do one more, which is 8 times 4, which is 32. And now to identify the least common multiple, actually I want to do one thing really quickly before we do that, which is we need to add these 3 dots at the end, right? And these 3 dots are called the ellipsis. And this just indicates to us that it goes on forever, right? So obviously you can keep writing multiples, you can keep writing these multiples, but that's not a good use of our time. We're just looking for the least common multiple, so that's all we're going to need, right? So now we look through these numbers here, and we think to ourselves, okay, well, what's the same, right? So we see a 24 is here, a 24 is here, and nothing before this is common in both of them, right? So if you're looking before this, you're looking at 18 or 12 or 6 or 8 or 16. That's not common between 6 and 8. It's all the time different. So that is the idea. In this case, we would say that 24 is the LCM. Okay? So that is how you find the LCM. Again, I'm calling this the slow way because at this point, we're not using prime factors, right? So this is sort of the old way or the way you might do in school. Not using the prime factors, right? Now, the second key concept today we're going to talk about is called the greatest common factor. Let's go ahead and highlight that. And the greatest common factor is a situation where we look at the factors. So this is the multiples over here. We did the multiples. So now we're going to do the factors over here. And we're going to then find what the biggest factor is between the two factor sets, right? So let's think about the factor sets of, again, 6 and 8. So thinking of the factor set of 6, what are the different factors of 6? Well, 6 Let's use red for that. Right? We know obviously the first one's going to be 1 and 6. They're going to be both divisible by 1 in themselves. And then for the next one, we're going to be using 2 and 3. We know that 6 is even, and it is even because it is a multiple of 3. And that's it. There's no more factors. For 8, we have a similar story where we have 1 and 8. Whoops. We have 2 and 4. 8 is not divisible by 3, and 4 is right there, so we don't need to do any more. So let's just close that off. There we go. And notice that there is no ellipsis here. And this is because the factor set obviously doesn't go on forever. You can have thousands of multiples for every number. In fact, you have infinite multiples for every number. But the factor set is a closed set. But over here, we can identify that the biggest factor that's common among these is 3. Is 2, because these are both even numbers. Bang. Right? So we would say that the GCF is equal to 2, because that is the greatest factor that is common among both of them, right? Now, there's a problem with this way, right? Obviously, we talked about it before. It is the slow way. It takes a long time to do this, and it's really, really inconvenient, because if you're going to do something this slow, tiring, sort of drawn-out way, it may not work. We use 6 and 8 in both of these examples today, but what if the example was like, 30 and 40, for example? If you're going to write out all the multiples of 30, you'll be here all day. So there has to be a faster way of doing this that applies to bigger numbers. So let's talk about that. All right, so now we have an improvement, finding the LCM and GCF, but this time using the fast way. And to really demonstrate the vigor of this question, I want to instead prime factor some relatively big numbers, some numbers that you may not have really worked with in the past, and I want to show you how this is going to work with numbers that you may not really expect in the beginning. So let me quickly grab my calculator here. Just give me 1 second. All right, we're back. Here is my calculator. We're back. Here it is. And so let's go ahead and first things first, the very first step, anytime you want to do it the fast way, is you need to prime factor. That's always going to have to be the number one thing you're going to need to do. Right? So prime factor, you're going to need to do that first. That's going to have to be number 1. So let's talk about, well, how would we do that? So for 420, this was actually the example that we did last week. I talked about the king of all questions. So I'm not going to redo how we prime factor it. If you're looking for some help on that, please watch the previous video. So what we will do here is we will just write out the prime factorization. Let's just quickly give this a bit of a wipe. Oh dear. Okay, so 420 equals to what? Well, from last week we know it equals to 2 squared. I'm just copying our last week's results. Times 3 times 5 times 7 squared times 11 times 13. Bingo. So it's a pretty big prime factorization. So that's going to be one of the reasons why I want to use this number. I want to really show you that it's the fast way, but really it works well when we have large numbers. Okay, let's do the similar thing for GCF. For 44,100, right? So let's go ahead and prime factor it quickly. So here's 44,100. Now, using my terminal zeros trick from last week, again, watch that previous video if you haven't yet, we know this is immediately going to be divisible by 2 squared times 5 squared, right? And then we can lower these two terminal zeros because every zero gives us 1, 2, and 1, 5. So that's actually, now we have 441, right? 441, if you're familiar with your perfect squares, this is actually a perfect square. So if we take the square root of 441, we actually get 21. So 441 is equal to 21 squared. And if we have 21 squared, we know this is going to break up into 3 squared times 7 squared, right? So now we put all of this together here, and we know that 44100 is going to equal to 2 squared times 5 squared times times 3 squared times 5 squared times 7 squared. Okay, and we don't need this anymore. This is just our basically our rough work. So let's go ahead and erase that. And I'm just going to check quickly if that is the correct prime factorization, and indeed we are correct. We are good to go. Okay, so now here I have the key, right? I really want you to pay attention to this because this is probably the one of the most effective ways I've seen of teaching LCM and GCF. When you're looking for the LCM, right, obviously we're going to be comparing the prime factorization of two numbers, this one and this one, right? So for 420, think of having a very large party, right? When you have a large party, you basically want to invite everyone. Even if they show up alone, you want to invite anybody and everybody that can possibly come to your large party, right? It's one of those big galas or one of those big balls where you want to invite everyone, right? So let's think about it. Let's compare these two prime factorizations first of all. So I'm going to write them a little smaller here. So here they are, same prime factors. I just wrote them a little bit smaller. And when we go ahead and we make the calculation for the LCM, let me change my color to this beautiful blue here, right? We want to include anybody and everybody. So we have a choice between taking a 2 squared and a 2 squared. So in this case, we don't really have an option. We're just going to pick 2 squared. But I'm going to show you in the next step. So in the next step, we have an option of picking a 3 or a 3 squared, right? So I'm going to go big or go home. I'm going to pick that 3 squared there. And same thing for 5. We have an option on the 5 on the top and a 5 squared on the bottom. So I'm going to go with the 5 squared. Finally, for 7, I have no choice. I have either 7 squared or another 7 squared. So I choose my 7 squared. But now we have a choice here with this 11 and 13. They basically show up alone to this party. But remember, this is an inclusive time. You want to include everyone at this party. So you just add multiplied by 11 and multiplied by 13. And that's our LCM. Now we do have to actually do this math and find a number. So let's do that quickly. 2 squared times 3 squared times 5 squared times 7 squared times 11 times 13. And we achieve, wow, a huge number of 6,300. Right? Now imagine if we were doing this the slow way. We would have to write out all the multiples of 420, all the multiples of 44100, and you would have to do that countless times to ever get anywhere. Which sucks, right? You want to do your questions the most effective, the most quick way, and this is how we get that done. Alright, now let's set up a similar scenario for the GCF. So first of all, I have the strenuous task of writing out all of the prime factors again, so let's do that quickly. So here we go, I've done it. And let's use a different color as well. Let's change it back to, let's use this beautiful green here. So now we're looking for the GCF. Now for the GCF, instead of having that large party like we did for the LCM, okay, for the GCF, we are going to have, on the contrary, a very small, oops, that is the pen, I don't need the pen. That is the highlighter with the wrong color. Yes, perfect. Actually, that's still a bit too dark. Let's go with this. Woohoo! I did it. So, for the GCF, right, so we need to take this number and this number. Instead, we're going to have a very small, secluded, private party. Only people that have a companion or the limited number of people are invited. So we're gonna go very, very small and very, very secluded. Let me show you what I mean. So for the GCF, right, in this case, that is not the same color. Let's quickly switch back to the other green. Right? We again have a number of choices. Between 2 squared and 2 squared, there's really no option, so we're just going to take 2 squared. But now we have a good choice. Between 3 and 3 squared. What shall we pick? Well, for 3, we're going to go with the small and secluded party. We're going to go only up to 3. We will not choose a 3 squared like we did for the other example, for the LCM example. Right? Same thing for 5. We're only going to pick up 5 because we have a choice of having only one guy in our party versus having 2 people in our party. And remember, the number of people who decide to join our party is represented by the exponent. Right? I want to see that explicitly so that everyone sees, so that everyone sees that. The number of people corresponds to the exponent. So we're always picking either for the LCM the most number of people or for the GCF the least number of people. That's how we're going to do this. Okay? For 7 squared, though, doesn't look like we have that much of an option. We're just going to pick 7 squared. But 11 and 13 in this case, they didn't come along with anyone. So they do not get to come to our GCF party. It's just going to be what we have right here. And now we do the task of actually plugging this into our calculator. Which gives us an answer of 2940. Right? Now, a couple of common observations. In the LCM situation, remember that we basically came up with and we got a bigger number. So 6306300 gives us a larger value at the end of the day. Right? On the other hand, the GCF gives us a smaller value. So that's a really easy way to check to make sure you did it right. All right. Okay, let's move on. Okay. Finally, we're gonna do basically an example. I pretty much did one on the previous slide, but I want to do an example of an LCM and GCF scenario. So what we're gonna do is we're gonna do the biggest one. So we're gonna do the big dog question here. we are going to do this question here. And these two I will assign as homework. Alright, so we have 1584. And we have 2275. Right? What's the first step going to be? We have to prime factor. Let's go ahead and do that quickly on the side here. So we have 1584. Let's put these on the top so I have some space to prime factor. Sorry about that. And we have 2275. Okay, so for 1584, let's go ahead and do that quickly. We know that's an even number. It is divisible by 2. So let's go ahead and do that. That gives us 792, which incidentally is also divisible by 2, which gives us 396, which again is divisible by 2. Which gives us 198, which again is divisible by 2, which gives us 99. And at this point, it's no longer even, so we switch over to doing 3. And we get 33. We can do it again. We get 11. And we can, I guess we can do one more step where we put the 11 here, and that's a 1. And all these numbers to the left become our prime factors of 1584. So let's go ahead and throw them in. 2 to the power of 4 times 3 squared times 11. Right? And let me check that quickly. Yup, that is correct. Okay. Let's also do 2275 here quickly. It's not even, and we can do a quick divisibility check for 3. So 2 plus 2 plus 7 plus 5 gives us a value of 16. It's also not divisible by 3. But we know it's divisible by 5 because this last number here is, of course, a 5, which means we're good to go. 2275 divided by 5. That gives us 455. Which is, of course, once again divisible by 5, which gives us 91. 91 is a very common number in Spirit of Math. 91 is 7 times 13. So if we divide that by 7, we get 13. And we can divide this by 13 again, and we get 1. So again, whoops, that is not a very good bracket at all. Let's put this in as our second prime factorization. Okay, and we can erase all of our rough work for now. Okie dokie. So let's go ahead and continue on with this this worksheet here. So let's find both the LCM and the GCF. Now this is actually a very unique case. When we're looking for the LCM, right? If we look at this, remember the LCM is the big party where everybody's invited. So 2 to the power of 4 is good to go. 3 to the power of 2 is good to go. 5 squared is also good to go. And also our 7 times 11 times 13, right? Because remember, everyone's invited, right? But notice one thing. Basically, we never really had to make a decision because there was never a situation where there was like the same number. We were never really picking between two of the same exponents with the exact same base. We were never really picking. So pretty much the LCM, let's go ahead and just multiply this number straight up. So we have 2 to the power of 4 times 3 squared times 5 squared times 7 times 11 times 13. We would get 360, 36,000. Sorry, 360, 3600. But notice one more thing is that if we just did, for example, 1584 multiplied by 2275, we get the same value, right? We get this value. So what does that tell us? Well, let's do one more thing. Let's do the GCF, and then I will tell you what this tells us. So, in calculating now the GCF, let's go ahead and take a look. So we have here 2 to the power of 4. There's nothing that matches, so we can't really take that. 3 squared, again, nothing that matches. We can't take that. 11, 13, 7, 5 squared. There are no matches. Right? Everyone's arrived by themselves, basically. You can imagine like 2 comes by itself, 3 comes by itself, but there's no 3 in one and 3 in the other one that come together, right? That doesn't happen. They kind of all come separately. There's no common base, right? There is no common base. And if there is no common base, we can't do a GCF. In fact, the GCF in this case, we say if there's no matches, it's equal to 1. And when the GCF is equal to 1, this has a special name, which is relatively prime. Right? So we would say that because of what happened in the situation, these two numbers are experiencing what is known as being relatively prime, because their GCF is equal to a value of 1. Right? So I've done this one, and you're going to be responsible for doing this one and doing this one. And here's a hint, none of them are relatively prime. So you're going to have to go back to our technique that we discussed on this page to really figure out how to do that, right? And again, if you're having trouble, watch the video again. That's going to be a really helpful resource for you guys moving forward. That's it. So it's now time to go ahead and try some different questions. And that concludes what I want to speak to you today for the most part. Let's just... and that's that. So I hope you really learned how to find the GCF and LCM, both the sort of slow way and the sort of more quick way. And I will see you guys in the next video.